Hello everyone, I am Prashant Kumar, pursuing BE at Sri Venkateswara College of Engineering. Today I am going to explain about the topic quicksort algorithm. Now having a look through table of contents where we are going to learn about quicksort algorithm, how quicksort works, partitioning in quicksort, quicksorting the list, example of quicksort, recursive quicksort implementation, illustration, time complexity, performance analysis of quicksort, advantages, limitations, and variations in quicksort. Now, having a look through introduction, quicksort is a widely used sorting algorithm. It follows divide and conquer approach to efficiently sort a list of elements. It has an average time complexity of 0. Quicksort is a highly efficient sorting algorithm that uses divide and conquer approach to sort items in a list or an array. The basic idea behind quicksort is to select a pivot element from the list and partition the other elements into two sublists according to whether they are less than or greater than the pivot. How quicksort works. Quicksort selects a pivot element from the list. It partitions the list into two sublists based on the pivot. Elements smaller than the pivot are placed to the left and elements greater than pivot are placed to the right. Partition is done recursively on each side of the pivot after the pivot is placed in its correct position, and this finally sorts the array. The key process in quicksort is a partition. The target of partitions is to place the pivot at its correct position in the sorted array and put all the smaller elements to the left of the pivot and all greater elements to the right of the pivot. Partition is done recursively on each side of the pivot after the pivot is placed in its correct position, and this finally sorts the array. Partitioning in quicksort. Partitioning is a crucial step in quicksort. It rearranges the elements around the pivot. The pivot is placed in its final position with all the elements to its left smaller and all the elements to its right greater. Quicksort algorithm so as to sort the list. Taking an example as EXAMPLE. Here we have an initial unsorted array, that is like left is not less than pivot stop at current position only. Right greater than pivot move right to the left of the direction where E and L gets mismatched. Left is not less than pivot stop at current position only. Right greater than pivot move right to the left direction. Then following to the step 3, left is not less than pivot, stop at current position only. Right greater than pivot, move right to the left direction where E and A gets mismatched, like they interchange. Left is not less than pivot, stop at current position only. So the both left and right stop at the current position, then swapping of left and right takes place, where A, which is smaller, like in alphabetically smaller, comes to the first position and E moves on to the third position, while another E acts as a pivot at the last. Left less than pivot move to the left direction, right is not greater than pivot stop at current position only. So X and D gets mismatched where E is alphabetically smaller compared to X, so it comes to the second position. So the left greater than pivot stop at the current position only. So right is not greater than pivot stop at current position only. So both the left and right stop at the current position, then swapping of left and right takes place. So similarly this process continues where all those gets arranged alphabetically correctly. So the two arrays, left subarray hold initial alphabets, right subarray hold final alphabets. Applying the same process of quicksort on the left and right subarray separately, then there will be a final of XMPLE, which is a sorted array. Then the new pivot takes place which was kept separated at last, the E. So the value of new pivot is greater than the old pivot, hence swapping them, EMPLX becomes as E, which acts as a pivot, then MPLX. So the new pivot is given, so the value of new pivot is greater than the old pivot, hence the swap takes place, MPLX. So the P and L goes on left and right where X acts as a pivot. So the value of new pivot is not greater than the old pivot, hence no need of swapping, where MPL and separated as X, then L acts as a pivot where M left and right pivot becomes as L, then LPM, where the remaining things are the MP. So the finally combining the result so as to get the sorted array where it is written as AEELMPX. So this is the final result after sorting a given unsorted array. Moving on next slide where we have another example of quicksorting. So let us understand the working and partition of quicksort algorithm with this another new example where we are going to consider ARR as 10, 80, 30, 90 and 40 where this is unsorted. So comparing 10 with the pivot as it is less than the pivot, arrange it accordingly. Compare 80 with the pivot, it is greater than the pivot. So compare 30 with the pivot, it is less than the pivot, so arrange it accordingly. Compare 90 with the pivot, it is greater than pivot. So it moves on, and so no swap, there is a end of traversal. Before there was swap 80 with the 30. So arranging this pivot in its correct position where 80 and 40 get swapped. So moving pivot to its correct position. So the final result will be written as 10, 30, 40, 90 and 80. Then 80 goes on swapping. So the final result will be 10, 30, 40, 80 and 90. So recursive quicksort implementation. Quicksort is implemented using recursion. After partitioning, quicksort is called recursively on the left and right sublist. This process continues until all the entire list is sorted. Illustration of quicksort. As the partition process is done recursively, it keeps on putting the pivot in its actual position in the sorted array. Repeatedly putting pivots in their actual position makes the array sorted. So the below images understand how the recursive implementation of the partition algorithm helps to sort the array, where 10 and 30 partition around pivot 30 is done, 90 and 80 partition around pivot 80 is done. So the pivot partition around pivot 40 which would result in 10, 30, 40, 90 and 80. So time complexity. Here we have three cases: best case, average case and worst case. In best case we have omega n star log n. In average case theta n star log n. In worst case we have 0. Auxiliary space is also 0. We do not consider the recursive stack space because if we consider the recursive stack space then in the worst case quicksort could make 0 nested recursive calls and will need 0 auxiliary space. Performance analysis of quicksort. Quicksort has an average and best case time complexity of 0, that's n log n. However, in the worst case scenario, it can have a time complexity of 0, that is n raised to 2. The worst case occurs when the pivot is always the smallest or largest element. Here we have a figure which shows the complexity summary where the sorting algorithm, best case, average case and worst case of all the sorting methods which we use like selection sort, insertion sort, bubble sort, merge sort, quick sort and resort, and accordingly their best case, average case and worst case, but actually the quick sort has the best case compared to other sorting techniques. Advantages of quicksort. Quicksort is widely used due to its efficiency. It is an in-place sorting algorithm requiring only small amount of additional memory. Quicksort performs well on average and best case scenarios. Similarly, here the figure shows where that is the first insertion. Similarly, after all the iterations like swapping method, the array will get sorted according to the order. Limitations of quicksort. Quicksort is not stable, meaning it does not preserve the relative order of equal elements. The worst case time complexity of quicksort can be concern for large datasets. Quicksort is not suitable for linked lists or already sorted lists. Here we have figure which shows in place quicksort. The algorithm input like sequences ranks I and R. Output is sequences with the elements of rank between I and R rearranged in increasing order. Also the algorithm where if I L greater than or equal to R return I a random integer between L and R x dot element at rank I. And also the quicksort can be implemented it to run in place. In partition step we use replace operations so as to rearrange the elements of the output sequence such as element less than pivot have rank less than h. The quicksort variations. Various variations of quicksort have been developed due to address limitations. Randomized quicksort randomizes the pivot selection to mitigate worst case scenarios. Dual pivot quicksort uses two pivots so as to improve performance. Moving on to the last slide where we have conclusion. Quicksort is a versatile sorting algorithm with high efficiency in most cases. Understanding the pivot selection and partitioning process, it is very important for optimizing the performance. Considering the characteristics of the dataset and choose appropriate variations of quicksort when we are necessary. Thank you for watching the video.